Okay, so here's a problem similar to what we've been doing. It wants the displacement at D, which is this free end. That's a cantilever structure. You can see it has a combination of a uniform load and a point load. And also, you'll notice that a little over halfway through, the moment of inertia drops down by a half. So there's a heavier duty beam over the first 12 feet and then a lighter one over the last 8 feet. So we'll talk about how to handle that. The first thing we have to do is write real moment expressions for this structure. How many do we have to write? Can we write one continuous moment for the whole structure? No. Because of this applied force, we'll be able to write one that's good from 0 to 6, and then a second one that's good from 6 to 20. Let's think about that. So I'll need to make a cut somewhere here between 0 and 6. You want to work the left side or the right side? This one might give you some pause to think. If you choose the left side, okay, but you have to find these reactions. Not hard, but you do have to find them. That takes some work. If you choose the right side, you do not have to find the reactions. But you do have to deal with some kind of odd dimensions. I don't know which one you guys want to pursue. Which one do you guys want to pursue? Left or right? All right. Tennessee electors again. I love this. What'd you say, Mr.?
Right.
Right. Let's go right. Since no one seems to care one way or the other, kind of like the election, we'll move forward. So if I cut it here between 0 and 6, I'm going to look at this side of the free body diagram. So this will be my real moment. It's still going to be valid from 0 to 6, except this is what my free body diagram is going to look like. That is 1.2 kips per foot. And then somewhere like right about here, I have a 6 kip force. Now remember, we're cutting it at some distance x. So what's the end piece? What's the length of this? 20 minus x. What would be this distance right here? Six minus x. This little distance here from the cut to the force. Remember, the cut is the part that's moving, the force is not. So at x equals 6, it should be 0. So this should be 6 minus x. See that? So that is the challenge of this particular way to go. And then, of course, we have our internal bending moment. Also, to make things a little easier for me, I'm going to get the concentrated equivalent force. So it's a rectangle, base times height. So that would be 1.2 times 20 minus x. And what's the distance to that? Well, it's the distance divided by 2, which would be 20 minus x over 2. Okay? So all I have to do now is sum the moments. So let's sum the moments at the cut. Make sure it's in equilibrium. So starting here on the left side, that moment is positive or negative with my sign convention? Negative. This 6 kip force creates positive or negative moment about the cut? Negative. So it'll be 6 kips times 6 minus x feet. What about the concentrated equivalent? Positive or negative moment? Negative. 1.2 times 20 minus x. And the moment arm? 20 minus x over 2. That looks like fun. So obviously we could multiply all that out and end up with a quadratic. I'm not going to do that. I'm just going to leave it alone. So move the moment to the other side. I get all that times all that. I can package together a little bit neater. That 2 will come there. Oh, I missed a minus sign. So this would be 0.6 times 20 minus x squared. Does it work? Well, I don't really know, do I? Because it's only valid from 0 to 6. Do I know the moment anywhere between 0 and 6? I do not. Now, I would know it at x equals 0 if I had my reaction, but I did not get that. So hopefully at x equals 0, you could compute it. But you could go back and check it if you wanted to. Okay, so the next moment I need is somewhere between 6 and 20. Let's say I'll cut it here. Left or right. We've already gone right. Let's continue to do that. So the moment from 6 to 20 so when I look at that free body diagram, I still have my distributed load, or the piece of it. It's still 1.2 kips per foot. The distance to the cut is x. The remaining piece I have is still 20 minus x. I still have my internal moment I'm trying to find. And I'll take that distributed load and get a concentrated equivalent force, which will be the area of the curve. Looks just like the one we had before, 1.2 times 20 minus x. And the distance from the cut, 20 minus x over 2. So when I do my moment here, it's going to look very, very close to the one I calculated previously, except I won't have this term in it. So starting with the moment, my moment is negative. The moment about the cut created by this force is also negative, so the force is 1.2, 20 minus x. And of course the distance to the centroid is 20 minus x divided by 2. So when I solve for the moment equation, I get minus 0.6 20 minus x squared. Now this one I can check, right? Because I do know the moment somewhere between 6 and 20. Where? Yeah, the free end. What's the free end? What's the moment to free end? 0. That's when x is equal to 20. And you see when you put in x equal 20, you get 0. So that seems good. We're out of time. So what I'll do is I either can pick up here on Tuesday, or I can finish this problem and just post it. What do you guys want to do? Let's see a show of hands. Raise your right hand if you want me to finish this problem and just post the solution. Or maybe we should do one or two. Right hand for that. Left hand for we'll just pick up here on Tuesday. Oh, it's not hard to know. Everyone raised all the same. Right hands first, then left hands. Ah, the left wins. How unusual. All right, we'll stop here.